Good morning. This is the second video lesson that I shall be presenting for Learning Outcome 11. As you would have noted, the first video lesson was also divided into Part 1 and Part 2. I shall also be doing the same with the second video lesson, and this represents the first part of the second video lesson. We shall be focusing on the assessment criteria as I have shortlisted. Okay, so basically, as you can see in the shortlist over here, we have assessment criteria which range all the way from 11.2a to 11.3f. Take your time to read these slowly. I shall briefly explain them. Basically, we shall start off this presentation by describing how a reaction rate can actually be measured and how we can interpret the meaning, if you like, of a rate of reaction. We can look at it as the rate of increase in product per second, per unit time. Or we could also look at it as the decrease in the reactants per unit time, per second. This presentation will focus very much on the experimental background required in order to demonstrate rates of reaction. So I'm going to focus on experiments linked to rates of reaction. And besides focusing on the experiments, I shall also be explaining how to interpret or how to explain the data that we obtain from such experiments and how to express them both in tabulated form and as graphs. I shall also be introducing to the idea of drawing more than one graph on the same set of axes. Okay, that is a skill that also is expected of you, especially at MQF level 3. Let's now move on to the next slide. So in this slide, we look at how the rate of reaction can actually be measured. And perhaps the graph that you have right here in the bottom left-hand corner, I shall indicate the graph as this one, okay, is an excellent summary of how we can understand a chemical reaction rate. Note that at time equals 0, okay, that at time equals 0, you have none of the product has yet been formed, and you have all of the reactants are still in place, reactants or reagents. So the reactants are still at the maximum level. We have given no time for the reactants to react, so there is no product so far. As time passes, the reactants will decrease in value. Notice there is a curve that slopes downwards. It's not a vertical line, and the reason is that initially there is a steep drop. Why is this? Because there are lots of reacting particles, as I had already explained in the previous presentations, okay, that are available for reaction. At the start of a reaction, you have your container contains reactants only and zero product. Therefore, there are a lot of reactant particles that are available for reaction. So it is much easier for them to collide and much easier for them to react because they meet each other so frequently. The rate of reaction is correspondingly high. As time passes, more and more of the reactant particles are used up, and therefore, as you can note, even from the steepness of the slope, the gradient decreases because less and less particles are available for reaction. However, at the same time as the reactants are decreasing, the products are increasing. Now, initially, once again, notice how the steep drop in reactant particles is mirrored by a steep rise in product formation. Why? Because as the reactants are very quickly consumed at the start of a reaction, obviously, the products are being very quickly formed. And likewise, at the end of a reaction, where the reactants are taking much more time to find each other and to react, and therefore there is a very slow rate of reaction, there is a correspondingly decreased rate of production of your product. Okay, so the product is also decreased in the rate of production, if you like. Over here, we have another picture, which is a reminder of what we have discussed in the previous presentations, where we looked at the factors that affect reaction rate. Over here, we have those factors identified once more. We spoke about temperature, catalysts, surface area, the state of matter, whether it's a solution or a gas. We spoke about molecular orientation. Remember what we said increases the likelihood of a chemical reaction taking place. It's not just the particles having sufficient energy, it's also their position in space. Concentration, pressure is linked also to the state of matter. We also spoke about light and how the presence or absence of light can affect whether a reaction takes place or not. Okay? Reaction rate typically has the unit per second. Anything that happens per second, any reaction that happens per second, or in other words, seconds to the -1. Okay, that is an expression of the rate of a reaction. It could be the rate of increase in mass of a product. For example, in the previous presentation, I would have spoken about the precipitation of silver chloride from the reaction between silver nitrate and sodium chloride. The rate of increase in mass of the silver chloride precipitate can be measured as grams per second. Okay? You could also measure the volume of a gas produced per second, as we shall soon see. Okay, I shall be introducing video demonstrations where gases will be produced within a given amount of time, and we can measure the rate of production of a gas in centimeters cubed per second. Let's now go on to our next slide. I would like you to become particularly familiar with both of the diagrams on my left over here. The reason is that these are typical setups that can be used not just to collect a gas resulting from a chemical reaction in the lab. I am sure that you would have come across both these setups, collection of a gas in a gas syringe and collection of a gas over water in year 9, when you were preparing hydrogen, oxygen and carbon dioxide in the lab. However, they can also be used to measure the rate of a chemical reaction. The rate of production of a gaseous product can be measured both by means of using a gas syringe and also by using an inverted measuring cylinder that is initially full of water, and the water is progressively displaced as more and more of the gas collects inside it. Now, there shall be a video demonstration, okay, later on in this presentation, in video lesson 2, okay, where you shall actually observe the demonstrator, the English demonstrator, using both of these methods. Then we shall look at the data that he obtains from the experiment, and we shall see how we can analyze such experimental data related to a reaction rate. Okay? We should now move on to our next slide. However, before doing so, I wished to also indicate a typical chemical reaction that could be used to investigate rate as production of gas per unit time. And a very classic example is the one where we react calcium carbonate, typically in the form of marble chips, with dilute hydrochloric acid, it will generate a steady flow of carbon dioxide gas, which can then either be collected in the gas syringe, as I just said, or using the inverted measuring cylinder. Do note that there is a slight error if using the collection over water, since carbon dioxide is partially soluble in water. Just be aware of that. Let us consider the reaction which I have just introduced, the reaction between calcium carbonate and hydrochloric acid to give carbon dioxide. And let's consider the table that we have right over here on the left. Note that initially, in the first minute, there are 34 mils of gas being produced. 34 centimeters of carbon dioxide gas are being produced. However, in the second minute, just another minute has passed, right? The increase in volume is just 8 centimeters cubed. So although the time has doubled, we do not get 34 multiplied by 2 centimeters cubed. So after the first minute has gone by, the reaction has already dropped in rate. The rate of production of carbon dioxide is no longer 34 centimeters cubed per minute. Between the first and the second minute, only 8 centimeters cubed per minute were produced. And if I had to go to the rate that exists between the second and the third minute, the rate keeps on dropping. Notice, this time it's 42 and 48, so it's 6 centimeters cubed produced in that minute of time. And once again, if I had to examine the third and the fourth minute, in that 1 minute, only 2 mils of gas are produced, and between the fourth and fifth minute, no gas volume at all has been produced, meaning that the reaction has now stopped. This basically is an experimental data proof, if you like, of what I initially said, that at first, since you have lots of the reactants, and I remind you that our reactants in this particular case are the marble chips, the calcium carbonate granules, okay, that are reacting with the hydrochloric acid. I am not balancing out any equation. All I shall be doing is representing the reactants. The reactants are those two. Initially, at the start of a reaction, there is plenty of the carbonate, plenty of the acid. As the reaction proceeds, as the first minute goes by, more and more of the carbonate, more and more of the acid is consumed. And since they are being consumed, there are less available particles of the carbonate and less available acid species available for reaction, such that the rate is much reduced after the first minute has gone by. Notice the setup, which already was introduced in the previous slide, that we could use to measure both the total volume of carbon dioxide which is produced after a certain amount of time. But more importantly, in this type of chemical reaction, where we are dealing with rates, we shall measure the volume produced after, for example, 10 seconds. So after introducing the acid and quickly sealing the bung with the delivery tube, okay, such that we instantly start to collect the carbon dioxide gas in the syringe, we've got the stopwatch. At time, for example, 10 seconds, we stop and we record the volume in the syringe. Okay, it can be done, as we shall see. Okay, there is a demonstration that shows you how this could be done, so that you can measure the volume of gas generated after 10 seconds, 20 seconds, and 30 seconds. And you will note this progressive drop in production of your carbon dioxide gas. Let's now move on to our next slide. I have once again put down the table so that I can further build on the explanation that I gave in the previous slide. This makes it easier to understand, and we split up the explanation as required. I will read through the text that you have in the two sentences over here, and I will explain their importance, okay? If we had to look at the table, we should note very importantly that the reaction is complete after 4 minutes. Okay, notice, after 4 minutes, at time 4 minutes, I have 50 centimeters cubed. Okay, so at that point, if I had to actually plot the data, sketch the data, okay, I would have volume of gas in centimeters cubed on the y-axis, okay, and I would have time in minutes on the x-axis. Okay, so let's put down the time and let's put down the unit as well. Always do that when labeling your axes. Always include the quantity, the variable that you're talking about, and also the unit. So basically, if I had to sketch the curve, it would look something like that. At the point where it just starts to level out, which would be approximately right over there, that would be time 4 minutes. Okay? At time 5 minutes, this is an important point because students frequently confuse this. Students sometimes give us the time when the reaction has stopped for some reason at time 5 minutes. Okay, they must, it is as if they must see a repeat of the 50. No. Since at 50, okay, at 4 minutes, okay, 50 was the maximum increase in volume, okay, and it did not go beyond 50, therefore, the reaction ended not at time 5 minutes, but at time 4 minutes. So that if we had to measure the average rate of production of carbon dioxide gas over 4 minutes, I would have to use this basic calculation. I would simply divide the 50 centimeters cubed or the 50 mils of carbon dioxide generated division by 4. That would give us an overall production of gas, okay, rate of production of gas at 12.5 centimeters cubed per minute, but it's an average over the complete period of the 4 minutes. As we said in the previous slide, the actual rate, minute per minute, will be very different from that number. This number is the overall. If I had to look at the rate of production of carbon dioxide in the first minute, since 34 mils of carbon dioxide were produced in the first minute, therefore, the rate for the first minute alone is 34 centimeters cubed per minute. Let's now go on to the next slide. It is not irrelevant to keep on emphasizing a very important point about the relationship between your table data and between how you shall interpret the data and represent it in the form of a graphical curve. So once again, do bear with me for having presented the table of data yet once more, because this time I shall be linking it directly to this graphical representation, this graph. Notice that on the y-axis we've got volume in centimeters cubed, always put in the unit, and we have time which is being measured in this particular instance in minutes. Okay, remember that the reaction was complete after the 4th minute, such that no production of gas took place between minutes 4 and minute 5. Now, if you had to plot the volume of gas on the y-axis, as has been done, against time in minutes, you will get this sort of line. It is a curved line. It is not a straight line up, and we already explained why. Initially, the reaction is fastest because there are many reactant particles. So the reaction progresses faster because there are many more collisions. Collisions are far more frequent, and as we said in the previous presentation, one of the factors affecting the rate of reaction is the collision frequency. As the reaction proceeds and more of the reactants are consumed, note that the gradient, the steepness of the curve with respect to the initial steepness, okay, we can put in steepness 1 or gradient 1, gradient 2, and gradient 3. Gradient 2 is flattening out. By the time we get to gradient 3, the reaction has stopped, and the reaction therefore does not produce any further gas. Okay? Since it produces no further gas, we say we have reaction termination. Okay? We can now move on to our next slide. Now, as I had explained also in the very first slide, you shall be expected to many times plot one curve from experimental data, and then you might be asked to also sketch curves on the same axis to show what happens if, for example, you are increasing the concentration of a reactant, or if you are, for example, increasing the surface area of a reactant, or, for example, at higher temperature. It is very clear that the steepness of the curve will vary. Okay? Now, over here, I have a particular example. Let's imagine we had the experimental data, the exact experimental data for the fast reaction. The fast reaction is the purple curve. We could then well be asked to state, for example, what we expect, what we predict the curve to look like if, for example, we used a smaller concentration of reactants. And besides stating, okay, in words, we would also be expected to sketch it out on a curve, okay, on the graph, okay. And as you can see, imagine that the purple curve represents a high concentration of reactants, so we can represent that as R, and the square bracket represents concentration of R. So for the purple curve, we have a high concentration of reactants where the initial rise, okay, in the amount of product is very fast. And if we had to compare that to a lower concentration of reactants, so we can represent that by putting in low R, okay, notice that the steepness of the curve, the rise per unit time of the curve, is significantly less than at higher concentration. However, do note that the eventual amount of product is equivalent, and the reason is that many times this type of reaction would involve the use of an excess of one of the reactants. Let me explain clearer. Let's imagine that we have the reaction between magnesium and hydrochloric acid. Okay? Now, we could have a situation similar to the purple curve if I used a concentrated solution of hydrochloric acid. So imagine the purple curve would be represented by 2 moles per liter of hydrochloric acid. It's quite concentrated, so the reaction is pretty high. And the reaction stops because all of the magnesium is consumed. Now, it is consumed fast. Notice that by the time we get to this point over here, let's call that time 1, the magnesium has been consumed by the moderately concentrated hydrochloric acid. There is an excess of acid, meaning there is acid left over after all of the magnesium has been consumed. And let's imagine, let's give it a number. Let's say that we had, for argument's sake, 5 grams of magnesium available. Now, the green curve is obtained by once again reacting 5 grams of magnesium. But instead of doing it with the 2 moles per liter of hydrochloric acid, I would do it with, for example, 1 mole per liter of hydrochloric acid. There is still acid left over, so there is still acid enough to react with all of the magnesium, and since all of the magnesium will react, it will still produce the same amount of hydrogen. In this case, I am measuring the rate as the rate of production of hydrogen, so the eventual total volume of hydrogen is still the same as when I had the 2 moles per liter, okay? But the rate at which it was produced is slower, so I will still eventually get to my equivalent level of hydrogen as when I used the higher acid concentration. But I will get there in a longer time because the acid is less concentrated, and since the acid is less concentrated at 1 mole per liter, the frequency of the collisions is also less.